Well, good afternoon, everybody. It's a pleasure to introduce Dr. Giovanni Fanchini of the Department of Physics and Astronomy and the Department of Chemistry at Western University as our WIN seminar speaker today. Professor Fanchini holds a Canada Research Chair in Carbon-Based Nanomaterials and Nanoelectronics at Western, and he has been working for more than a decade on different types of carbon-based nanomaterials, including diamond-like carbon, carbon nitrides, boron carbide, carbon nanotubes, blends of fullerenes and photoactive polymers, and since 2006 he's been working on graphene. His research focuses on the applications of graphene-based materials in innovative solar cells and for thermal management applications. Before joining Western in 2010, Professor Fanchini worked as a solar cell scientist at the Molecular and Health Technology Division of CSIRO in Melbourne, Australia. He also spent a period as a postdoc at Rutgers from 2005 to 2008 and at Politecnico di Torino in Italy from 2003 to 2004. He was awarded a PhD in physics from Politecnico di Torino in 2003. So please welcome Dr. Giovanni Fanchini for his talk entitled, interesting talk, How to Make Puzzles with Graphene Platelets, Transparent and Conducting Graphene Thin Films, and Graphene-RNA Nanocomposites.
Yeah, thank you so much Arthur, for your kind introduction. It's really a pleasure to be the first one to speak in this room. Is that correct, right? In this outstanding building, there is really nice things I see going on in Waterloo, exciting things, so it's very exciting for me to be here. And let me just first introduce my collaborators. I just joined Western quite recently, 2 years ago, and my group is not really that big at this time, but is growing, and many of my students are really excited and exciting students to work on with. For instance, Shafiq, who is doing a lot of thermal management on graphene, Reg and Sebastian that are doing solar cells applications of graphene. There are a couple of people who are making processing or studying defects in materials, Arash, Faranak, Lisa. And I want to thank, of course, the very generous support I had in Canada for starting up this work on graphene and continuing it on a different note than what I was doing before at Rutgers and in Australia has been really, really exciting time. Well, you know, graphene has been the 2010 Nobel Prize in physics. That was exciting. You think at the new material. I was always curious. You know, it's pretty easy to do it. So I was curious to see when has been the first time that somebody actually made graphene. And I went back in time reading around in old papers or something like this. The first report that actually has been reproduced recently and is clearly graphene, or even better, graphene oxide, has been a Victorian paper in the UK, University of Oxford, 1859. So you see, not really 2005, 2010 or something. Graphene has a long way, really, in the history of material science. And so that's just a suggestion. Maybe I used to tell that to my students. Your success is not really to invent new things, but to get old things working better and at the right time. And that's what happened to graphene. Basically, what this guy, Benjamin Brodie in Oxford, 1859 did. Well, at that time, the table of elements wasn't really there, really, not at all, wasn't known. And the guy was curious to see if there was an oxide for graphite. They were suspecting that graphite was made out of carbon, actually, but that was just the beginning. So he took some graphite. Some of it was actually coming from Canada, from New Brunswick. He took some from Sri Lanka, some from Greenland, I believe. He put that in the flasks and he mixed it with sulfuric acid and what was the stronger oxidizer at that time that he called potash chlorate, actually potassium chlorate now we will say. And he put these flasks on the pale sun of England. You know, it's not really strong, but after a while he have seen this graphite dissolving in this mixture of acid and oxidizer, giving a yellow pale color, and he was thinking, oh, I got a new oxide. I was actually graphene. And he put some on a glass slide of a microscope. He went to Cambridge where there were better microscopes at that time. And eventually his colleague in Cambridge said, oh, you have very thin flakes, so thin that we cannot measure the thickness. Obviously, the thickness was angstrom, less than 1 nanometer. They couldn't know at that time. There was no way with optical microscopes. And the guy drew him a shape like this. From the crystallographic orientation, I believe that there is something like ions, molecules, you know, Avogadro work at that time was known already, of this shape. He was indeed correct. You see, old guys sometimes did an outstanding job, and that was the start, actually, of graphene. Then, for 100 years, everything was forgotten. Then, little by little, in 1946, and so on, some theorists, Wallace, and so on, started to work again in this from a theoretical perspective. But that actually was the first report of graphene oxide, so long way. So why this exciting field resurrected again in 2005, 2008, and so on? Well, there are various reasons. One is that graphene has a very exciting new physics into it. And that's one reason. But we always want to turn physics into the realm of practical applications, right? And one thing is obviously that this ultra-thin material has tremendous transport properties and tremendous optical properties because it's thin, so can be a good alternative for transparent conductors, right? And I will say conductors, not just electrical conductors. I will show it later on. Also transparent thermal conductors that are even more rare than transparent electrical conductors. Think a little, there are very few materials that they are transparent and conducting. I mean, the youngest of you guys will think every metal is not transparent unless it's ultra thin. In fact, the most popular transparent conductor in business is indium tin oxide, or ITO. That is a doped tin oxide that needs indium. Indium is a very rare element. There is some in Canada, in North Canada, Baffinland, that area, but you know, it's very difficult to go mine there. And indium is getting more and more scarce and more expensive. You see here, this is the price that skyrocketed more or less by one order of magnitude from 2002 to 2007. Then it dropped, now it starts to go up again. Don't have the very last figures. And the consumption also raised. But it's not just the consumption, it's just this. You see, the increase in cost is higher. That means it's getting more and more scarce, this material. And incidentally, has other issues. One is that if I have an indium tin oxide tin film on a piece of plastic and I continue to bend it multiple times, it degenerates and degrades from cracks, dislocations, defects, because it's a crystalline material. And there is another issue that is a good electrical conductor, but is not such a good thermal conductor. We can be useful for other things. So basically, there are a number of reasons why you want to replace this indium tin oxide and this indium with something that is cheaper, more abundant on Earth. Carbon is very abundant, you understand. Maybe with a better thermal conductivity, with a better flexibility. So here we go. This is why these materials get more popular. So I started to work, you know, I'm Italian, and I started to work on solution processed films for replacing ITO with carbon nanotubes. that are also tremendous conductors and have good optical properties. And I was always making an analogy, how I prepare my carbon nanotubes films that basically look like spaghetti spread out on a table. Well, you generally, how you cook spaghetti, you put spaghetti in water, you boil it, you make a bit of suspension from canned spaghetti, then you filter them somewhere, and then you dish them. And you have spaghetti on your dish, on your table. So when it comes to graphene, so how you implement this in practice in a lab? I mean, not in your kitchen, I mean. Well, you start from canned graphene or carbon nanotubes. You see, here we go, this carbonaceous material. You suspend them in water or organic solvents, maybe with help of something. Like here we go, the suspension. You vacuum filtrate. You see, the job is pretty easy in a lab apparatus on a sacrificial filter membrane that is placed here. So you really spread out here. This is the sacrificial filter membrane with some graphene or carbon nanotubes on the top. You see gray one. This is the membrane. The membrane can be applied on any substrate you want. Here there's a glass slide inside this Petri dish. And eventually this is dried in contact with the substrate that can be transferred to the substrate, and the sacrificial membrane is generally etched by means of a combination of solvents. The standard one is acetone and methanol, so easy things, but other solvents are possible if your substrates have compatibility issues with the solvents. There are other issues, other possibilities like dry etching to get rid of this sacrificial membrane. So you see, we'll literally print out any possible film from a material suspended on a sacrificial filter membrane, and that can be scaled on any type of substrate. So what's happening when we do these films by graphene? You see, carbon nanotubes are a bit like spaghetti. Well, you just do puzzles. So here we go, the title of my talk. Basically, assume you have a puzzle like this. This is how it looks like in atomic force microscope. You see you have patches, stripes, and so on. What's happening is that some platelets of graphene goes on your substrate in the vacuum filtration apparatus. So where one of these sticks, locally suction from the vacuum filtration apparatus stops, and the platelet goes nearby. Here is another animation. You have your graphene oxide suspension. You vacuum filtrate it. You have your graphene oxide. Exactly like this can be exactly Brody's solution of 1859. This is your filter membrane with a number of pores. You see you have suction. You have one layer going here. Where there is the first layer, the second cannot accommodate because here suction stop. And little by little, another comes here, another comes here. Of course, there will be overlaps. It's a patchwork, basically. But the system like this is scalable to any size. These membranes are produced up to wafer size or even bigger. So, well, this is an optical image of what's going on. Here you had a number of few layer graphene flakes, thicker graphene flakes. You can do pretty much a good layer of electronic grade material. And that's what we did in 2008 when we started to work with graphene oxide. Okay, you say, is graphene oxide? What is graphene oxide? This material that Brody got in 1859 that was very thin. Is just graphite? No, it wasn't just graphite. It's graphite decorated with oxide and carboxyl groups, hydroxyl groups, that keep it soluble in water, basically. So when you have your thin film on the substrate, it's time to get rid of these oxide groups, reducing the film. There are many ways to reduce these films, for instance, by heating it up, or by appropriate reducers like hydrazines. They're pretty good at that. And you obtain a film that is nearly graphene, with very little impurities. And how you can see that? One non-destructive way to see graphene that is very popular is Raman, and that's what we used in 2008. There is a typical Raman peak at 2800 centimeter minus 1 that basically is related to the vibration, the breathing of the graphene, of the rings of graphene in a honeycomb lattice. And the second order peak is, for electronic reasons, is very sensitive to the number of layers. If you pile up more layers of graphene, the peak tends to shift. So basically, from the position of the peak, you can really count the number of layers you are laying down on the substrate. Obviously, if you are filtrating more when you have done the first layer, you pile up more layers and you pass from single or few layer graphene into multi-layer graphene. And so you see this peak shifting up. This is the case where you have filtrated more, and you see you have area where you have more than 5 flakes. The average is 3 to 5 layers. Here you have areas where you have even single layer. This is a Raman map, so we are going step by step with a Raman microscope, and we are looking the position of this peak, and this is how it looks the film. It's a transparent conductor. Is this working like ideal graphene? You know, graphene as an ideal flake has been done for the first time by Scotch tape. Now it's pretty popular. Just you take some HOPG or something with a Scotch tape and you put it on the substrate. Of course, these flakes go randomly. It's not a large area film. They have outstanding properties. One of these is actually a gate characteristic. Graphene is a graphene-based transistor is ideally an ambipolar transistor that has a V shape in the gate characteristic, in the gate transconductance, that is basically mimicking the density of states of graphene, that is linear in the proximity of the Fermi level. Are our systems doing the same? Yes, pretty much. You see, you have a V shape, and the possibility to gate it, to do a transistor, depends on the number of layers of graphene that you have in your system. If you have just few layers, you have really a characteristic like an individual graphene flake. The more layers you pile up, the more the characteristic gets flat. That is basically what's going on when you have graphite. This is what people got when they were trying to use graphite. The only caveat, the only point to be reminded is that this patchwork doesn't have the mobility of the individual graphene flake, because of course they are junctions. So this is a new, exciting, completely different material. For instance, the mobility of this graphene film is comparable, just here is a set of electronic grade materials, to the one of hydrogenated amorphous silicon, not the one typical of crystalline silicon or carbon nanotubes or individual graphene flakes. This is the field effect mobility of a number of these materials. A nanotube film done in the same way has a higher mobility. But of course, nanotubes cost. Graphite to be exfoliated by these methods cost $1 per kilogram. At the beginning, there were concerns graphene is the most expensive semiconductor on Earth. That's not the case in this way. That's perhaps the cheapest and the most tolerant to impurities, which is even great because you don't need extensive clean room fabrication. But you see that this is graphene oxide, and you see it here. This V shape doesn't go to 0 as it should be if the density of electrons here goes to 0. That is the case of graphene. That is an ideal zero band gap semiconductor. And this is related to the fact that this graphene oxide is relatively full of defects that also are responsible for this relatively low mobility. That was the message I got when I started to work on these things in 2008. So when I started my new faculty position at Western here in Canada, I will show you later on during this talk how we can get a better mobility, how we can get a better material, and how we can shortcut this passage from graphene oxide that degrades the material, because most of the defects come obviously from this oxidation process. So here we go. How is the electrical transport of this system controlled? You see, there are patchworks. So the first thing you can think to understand the transport in these materials is percolation theory. We had used it before for carbon nanotubes. This is, yes, the typical carbon nanotube thin film, spaghetti on the table, is a percolation through sticks. that basically, or tubes, and the percolation threshold is very low. The percolation threshold is, by the way, the minimum concentration of nanotubes or flakes that you have on your layer that allow you to draw a continuous pathway along the film. How dense they have to be to do that? That controls your properties. How dense is your patchwork of graphene flakes? If you are below the percolation threshold, so these are sparse and individual and separated, the conductivity is 0 or tends to 0. At the percolation threshold, you start to have conductivity and increase above. This is generally expressed by a power law like this. The conductivity is equal to the conductivity of the individual flake, that obviously matter, multiplied by a power. F0 is the percolation threshold, F is the fraction of covered area that has to be above the percolation threshold, otherwise this relation is not true. At the percolation threshold, this term is 0, so you don't have any conductivity, and there is an exponent that is related to the dimensionality of the system. So, and here is a set of graphene thin films as a function of the area coverage. These are the platelets. A fraction f of the surface is covered by the platelets, here increased more or less from 0.2, 0.3, that is the percolation threshold for these disks, to virtually 1, and the conductivity increases in that way. Depends also on the conductivity on the individual flake. Quite incredibly, this relationship works also if I am plotting it as a function of the thickness of the graphene flakes. So if with IFM or with a profilometer, I try to determine the average thickness of the film, that increases if I am filtrating more material, if I am piling up more layers in my vacuum filtration apparatus, and you see I can go pretty thick. Again, I have a relation like this. So I have a critical thickness for which I have the onset of the conductivity. This is a remarkable consequence of the fact of the vacuum filtration apparatus, on the vacuum filtration system, because the more I am filtrating, the more layers I'm piling up. Not only I'm covering more area and decreasing the amount of voids remaining between the flakes, but I am piling up much more layers. And in fact, between F, the fraction of cover area, and N, the thickness, that I can easily investigate with atomic force microscopy, for instance, or any microscope, many form of profilometry, yes, I get something like that. How about the optical properties? We have said that, okay, we need conductors. Graphene can be pretty conducting, but we need a transparent material as well. How is the optical transparency of this? It's known that in individual graphene layer, was a nice paper of Andrei Game and Kostya Novosilov, transmit 98% of the light. So the transmittance is 0.98, pretty high. How it goes, the transmittance of films? Depends, in fact, on the thickness, on the average number of layers, and there is again a nice exponential decay. So it's 100% E minus N, the number of layers of the film, divided by M, that is the tip, is a number, is a decay constant in a way, that is about 50. So for 50 layers, the transmittance of my system goes to 30%. Why? Because E minus 1M, so when N is equal to 1, gets exactly 0.98. So a simple model like this tells you why the transmittance of these films decay exponentially, and there is more than that. You see that the transmittance is relatively constant. So, as it has to be, because here there is nothing that really depends on the wavelength. So if I put these two relations together, the percolation relation that we discussed above, and the transmittance of the films, which we did as a nice exercise when somebody asked me to write a review paper on this topic. This is a zoo, I withdraw the name of the authors just for privacy, but this is a zoo of solution processed graphene films published by some 10 or 15 groups all the way through the world. There are also ours in the middle. You combine these two things, you get the relation, the proportionality relation between F and N that we have seen before, that comes from the from the way the vacuum filtration method works, and you get a nice relation between the conductivity and the transparency. So there is a trade-off, you see. The more transparent, the less conducting, which is not fantastic in its own way. But of course, you can find an optimal trade-off for optical applications. And you see, this relation depends on A, that is this coefficient of proportionality that there is between transparency and conductivity. Basically, it's this between fraction of covered area and thickness. Basically, the slope of this curve. This depends on the degree of dispersion of your flakes in a suspension. If they are aggregated, so they stack all on the same place of the filter, they don't make a good puzzle because your kid is not so skilled to do that. A is generally pretty low, pretty high, pardon, and at that point, the trade-off is not very good. Depends on S0, the conductivity of the individual flake. You want flakes to be very conducting to have a good patchwork, but that's pretty obvious. And on that exponent, that is a measure of the dimensionality of the film, but is a minimal dimension dependence. So, since we have seen a little the basic electrical or optical properties of this film, let's see a couple of applications. We mentioned electrical conductivity. How about thermal conductivity? This is something I got interested here when I was in Canada, when immediately, at that time, some papers about the conductivity of individual graphene flakes blossomed. I wanted to know what's going on in our puzzles, that there are different materials, the junction matter. You see, our percolation model for electrical conductivity neglects the contact resistance at the junctions and works. Is the same for thermal conductivity? Well, I don't know. How we measure the thermal conductivity of these films to see if really we can use percolation theory also for studying the thermal conductivity of these films? Well, we have developed a system that is pretty user-friendly. It's a photothermal deflection spectroscopy apparatus. Basically, imagine mirage effect. You know, it's the effect that makes you, I mean, in a hot day in the summer, makes the pavement of your the blacktop of your road to be like shiny, like water, when it's far away in the distance. What's going on in that case? You have the sunlight, air atmosphere is pretty transparent, the sunlight illuminates and heats up the pavement, so locally the pavement gets hot. When it gets hot, the air near the pavement locally changes in density. It's almost an ideal gas, but many fluids change in density. So you have literally a lensing effect. The hotter, the less dense it is. And therefore, if I am illuminating a film with pulsed light, like I'm chopping light, I have pulses, boom, boom, of light that heat up a film in a photothermal fluid, in this cell here. Locally here I have a lensing effect, a gradient in density of the photothermal fluid. Can be air, but air is not a great photothermal fluid. It's a relatively poor photothermal fluid. There are fluids that are much more photothermal, like carbon tetrachloride. There are even photothermal fluids that are produced by companies. And so with the grazing laser, grazing the surface of the sample, basically you have a lensing effect, a deflection, when you have the thermal gradient. So if I am pulsing light, lights get really deflected, from this laser gets deflected, like this, after the pulse. And this can be measured by a position detector connected to the chopper or to the pulsed laser by a lock-in amplifier. That's the drill of doing photothermal deflection spectroscopy. Obviously, the deflection has a delay. Why? Because the sample has not an infinite thermal conductivity and not an infinite thermal capacitance. So it takes some time to heat up. So you can exploit, basically, the amplitude of this photothermal deflection spectroscopy signal. You see, this is the chopped light. This is the response, takes some time to go up and takes some time to go down, so there is a phase shift, for measuring the thermal diffusivity and the optical absorption coefficient, and the phase shift to measure the thermal capacitance of the system. If I have the thermal diffusivity and the thermal capacitance, I know the thermal conductivity. If the optical absorption coefficient, so the amount of light that is absorbed by the sample and dissipated into heat, is known, but this can be known if I know the optical properties of my sample that I can measure by UV visible measurements or things like this. So here we go. We compared, of course, for a while this technique with other techniques to make sure it works. It's simpler than them. You can also estimate if there is a thermal sink on the substrate, making a measurement on the other side to calibrate it. There are ways. I mean, this is a simple toy model. The actual model based on the equation of heat is a little more complicated than that. But basically, these are the ingredients. And what you find, anyways, is that while the thermal conductivity was increasing with the fraction of covered area and with the number of platelets, the thickness, you remember the two quantities were proportional, the thermal conductivity is decreasing, which is quite interesting because, you know, in metals, if you have a higher thermal conductivity, you also have a higher electrical conductivity. The two are bound by the fact that electrons in metals are responsible for thermal conductivity as well as for electrical conductivity. The more electrons you have, the more you have both. This is what is called, you may know, some of you that have a background in physics, Wiedemann-Franz law. There are other names for chemists. But here is the opposite, because the thermal conductivity of these materials is controlled by lattice vibrations, while the electrical conductivity is controlled by the few free electrons that there are in graphene. Graphene is a zero-band gap semiconductor, so by definition a material in which the number of free electrons, the concentration of free electrons tends to 0, while their mobility tends to infinity. So it's an interesting material. But there are just half of it, because there are also lattice vibrations that are responsible for this tremendously good electric thermal conductivity. That is decreasing, so we wanted to see why it was decreasing with the number of layers. The thermal conductivity of individual graphene flakes had been measured before by more complicated systems by Ballanding and other people at UC Riverside, and somebody termed graphene a thermal superconductor. This may be a little, what can I say, nice name for something that is partially true, however. Why the thermal conductivity is so high? But you see that anyways, the thermal conductivity is partially retained here, because we are getting, before we had 5,000, here we have as much as 2,000. That is still pretty good if you do the right thing with flakes that have very little defect density. What is responsible for the limitation of the thermal conductivity of individual graphene flake, or generally what limits the lattice thermal conductivity in a solid, are only collision between phonons. You cannot just have drift of phonons. If it was just about drift of phonons, phonons are quantized lattice vibrations, you may know. Thermal conductivity is infinity. You need to have phonons colliding each other, interacting each other, in order to limit the thermal conductivity of a crystalline solid. For an amorphous solid, you may have scatter with distortions, defects, other things. But this three-phonon process, so you have two phonons scattering and forming a third phonon, are extremely rare in hexagonal lattice like this. And that's the reason why it's really a sort of a thermal superconductor, or somebody may likes to call it that way. And of these processes, only a few of them actually limit the thermal conductivity of a solid. That they are the so-called unclap processes, so processes for which, if you represent a solid in the space of phases, basically you have the outgoing phonon scattered out of the Brillouin zone, of the periodicity of the lattice. These are the real three-phonon process that matter for limiting the thermal conductivity for a solid. In graphene, you have none of them. So you have to go to the fourth or the fifth order, collisions of 4 or 5 phonons to bring incoherence to these lattice vibrations and limit the thermal conductivity. That's why it's so great. But look what's going on if you don't have one layer of graphene. You can have out-of-plane phonons. And in that case, again, you can have, you see, this is a one layer of graphene. You have other layers. In the K space, in the reciprocal space, is basically the same. And you can have normal process or unclap process. Basically, the phonon excitation is scattered from one plane to another. These are really the processes that limit the thermal conductivity of graphite. That is incidentally pretty good. Graphite is a material for thermal management applications. You coat pistons with graphite like carbon or with graphite to evacuate heat better in cars. So these are the processes that limit the thermal conductivity. So here we go. When you have a junction, so you have twice as the thickness, you have the bottleneck of your thermal conductivity. While the contact resistance, electrical contact resistance, I mean, between two platelets was negligible, at least at room temperature. It's a different story if you go at low temperature. But if at room temperature, so the percolation theory was working for electrical conductivity, is not working anymore for thermal conductivity due to these interplane unclap processes like this. So you're scattering your phonon excitation to another layer. Of course, you need to have that other layer. If you have graphene, you have just one layer, and these processes are forbidden. And you have to go to the 5th order and so on. So the areas where you have 2n layers, where n is the number of layers in the individual graphene flake, are the ones that limit your thermal conductivity of graphene. And there is a formula that has been brought much before that graphene was coming popular. Clemens at UConn, in Connecticut, did these studies just theoretically before and came out with a simple relation that determined the thermal conductivity of these things. Depends on the number of layers. This is the Debye frequency of graphene, is a parameter. This is a cutoff frequency for these out-of-plane phonons involved in unclap processes. Basically, this goes down when you have more layers, because if you have more layers, you may have more incoherent vibrations between layers. So these unclap processes are encouraged. This number gets much bigger than 1, and the thermal conductivity goes down. Not so much, however, goes down in a, or better, no, this is higher, so in a logarithmic way, so goes down pretty easily, pretty difficult way. But anyways, there are the overlaps that, according to percolation theory, then the density of overlaps is F minus F0, is the concentration of overlaps that limit your thermal conductivity. When you overlap layers, there you have a bottleneck for thermal conductivity. While the n layers limit the thermal conductivity much less because they are thinner. And voids, of course, doesn't do anything. Edges can do something, however. So our model assumes that edges can be negligible, and that's an important point. So if you use a formula like this, that the actual thermal conductivity of your field is a parallel of the area with a thickness that is of 2n layers, so an overlap, and the other component of the parallel is the area where you have just one layer, one flake, you get a pretty nice relationship for the thermal conductivity using the Clemens formula that can be used. And that explains the decrease of your thermal conductivity. Well, if you're using just poor Clemens formula for n layers, the average number of layers, that doesn't explain a lot. The decrease is much slower. It's poorly logarithmic. So, very low, you see, almost a constant. You don't even realize that this line is a decreasing function on this scale. So when we had, I was mentioning before that when I left Rutgers, I decided to move a little away from graphene oxide. because there was a lot of defects. Defects lower the thermal conductivity, defects lower the performance of graphene-based devices. Defects are related to the fact that I have to use this treatment that is quite close to the treatment of Brody 1859 to oxidize graphene to make it soluble in water and vacuum filtrate it spaghetti style. And I didn't want to do, I wanted to still use the vacuum filtration method because creates films, very scalable with a lot of applications. But I want to do it with something that is a little better than graphene oxide. The other option to keep something suspended in a solvent, if it's not soluble, are surfactants. So, you know, chemical compounds that basically minimize the surface energy between a solid, an object, and the fluid that surrounds it. And for a number of reasons, I thought that ribonucleic acid was a pretty good surfactant for graphene. There were others used at that time. And one thing at Western that I was asked by collaborators was, can you make, please, these graphene films biocompatible to use in biodevices that we can put in the body? And they said immediately, no, graphene oxide doesn't work because you put in nitric acid, in sulfuric acid, in potassium chlorate, in corrosive things. Some of them will remain, for the body is not good. Think of something else, please, Giovanni. The other alternative is growing graphene by chemical vapor deposition on copper. That's possible, but also copper residuals are not nice to put in the body. Copper oxides are particularly weird. Reduced graphene oxide has the same problems of graphene oxide, but also hydrazine is not something nice to put in the body, even worse. So again, was about using surfactants that were biocompatible. One surfactant is that was very typically used for dispersing carbon nanotubes, and there were also a number of reports for graphene, was sodium dodecyl benzene sulfonate. It's a typical anionic surfactant, long chain. The problem is that it's corrosive. It's not really what you want to eat at lunch, at dinner. And so here I came with RNA, that is something that is a little more biocompatible. The difference between the various surfactants, like SDBS, that is anionic, is that RNA is a typical non-ionic surfactant. Typically, surfactants has a region, are chains, long organic chains, with a termination that is hydrophilic and a chain that is hydrophobic, sometimes vice versa. If there is a charge transfer between the two tails, you have surfactants that can be anionic or cationic. You can have deuterionic surfactants that have a dipole at the end of the chain. RNA is a typical non-ionic surfactant, so it was conceptually different from the surfactants tried above. That's what was intriguing me. And I knew for a few attempts that was working for carbon nanotubes, when DNA was used to sort carbon nanotubes. Basically, the trick is that every I won't say monomer, every group of RNA, every nucleotide has a charge transfer because it has a phosphate group that is negatively charged, and the base, every nucleotide in the RNA, that is most of these bases adhere very well to graphene because some of them have pi electrons and really have strong van der Waals forces. If, for some reason, these van der Waals forces are stronger than the van der Waals forces that make RNA to entangle, I can make it adhering to graphene. I can have it penetrating between the layers of graphite, and I can have exfoliation just simply by sonication. That's actually what we did, and we published this year in SBO, and was a pretty interesting thing. So here it goes again. We can get few-layer graphene for a number of RNAs from fungi or relatively cheap RNA. Of course, the type of RNA and the ability of this RNA to disentangle in water and penetrate in graphite is pretty important. I won't comment too much on the types of RNA that you use. Also, the defects on the graphite that you are using are pretty much important. And you have regions of these films where you have graphene, regions where you have RNA. So they're really graphene-RNA nanocomposites, in principle, that they are very different depending on the type of RNA I'm using for dispersing. When I vacuum filtrate, I don't just have spaghetti, I have spaghetti and sauce. In this case, the sauce is RNA that spread out. Some types of RNA generate with longer chains with more nucleotides that disentangle more, form a continuous layer, continuous film on graphene, something like this. Some other types of RNA forms literally chunks, bubbles, on specific locations of graphene where graphene we know is defective. And this creates some, in this case, a buoyant force that keep RNA suspended in, graphene suspended in water, and at the same time, this intercalation of RNA into graphene favored its exfoliation. So it's a pretty nice job. Again, if you use Raman as a check, you find out that when you vacuum filtrate just one layer of this suspension, you have single layer graphene with this 2D peak that I was considering before. Ignore these other 2 peaks of the Raman spectrum of graphene for this application. Is very downshifted, that means I have 1 or 2 layers. And in some other cases, if I filtrate more, I pile up more layers, I have a thicker graphene. Graphitic film. And you see I can go from very sparse to very dense. Very dense give me the spectrum of graphite, very sparse give me the spectrum of graphene. And obviously I always have around some RNA unless I remove it in some way, and there are ways that I will tell you now. These films, in these cases, since I have nanocomposites, the conductivity of my films also depends on the RNA that remains in the junctions. RNA is a pretty insulating material, right? So I have to remove it. One way is to heat up and reduce RNA literally in ashes. It goes away, and in fact the sheet resistance in the verse of the conductivity goes down, and the conductivity improves pretty much, even better than graphene oxide, so that works, just with temperature to get rid of RNA at the junctions. Other things I can do to improve the quality of these films is functionalize the individual flakes. So the conductivity of the individual flakes increase, the conductivity of my puzzle increase accordingly. I can combine these 2 treatments, and this is the best, of course. So an application that we have seen for this type of films, now we have seen what are the properties of these films, what they can do, what they can do not. The optical properties are very simple to understand just with a multi-layer model. The electrical properties require percolation theory to be understood. The thermal properties requires the inclusion of the junctions between the flakes of overlap to be understood. Let's see how we use, just in the last few minutes of this talk, these films as transparent conductors. A typical application when you need transparent conductors are thin film solar cells, where basically the mobility of the active material that needs to be cheap is small, so you need to have a sandwich, the 2 electrodes in sandwich to have the device to work. But imagine if you have a sandwich and you want to illuminate what you have inside, you need to have 1 transparent electrode. So here is the application. Another application of transparent conductors are flat panel displays, like my computer. With the standard solar cells we tested for compatibility are organic solar cells. Typically, organic solar cells are made by an acceptor that is fullerene or a soluble derivative of fullerene like PCBM that can be dispersed in organic solvents. You need a donor that is typically a conducting polymer. Very popular choice is polyethylthiophene of the regioregular form that stacks and gives a good mobility. And this is typical donor material. For these materials, the exciton diffusion length, so if you produce in this material an electron hole pair illuminating it, the diffusion length is very small, much smaller, much shorter than in inorganic materials, for a number of reasons that there are, again, related to this curious coupling between electrons and phonons that we have seen that is responsible of the thermal conducticity of graphene, basically. So the exciton travels very little in this material. So you need to prevent radiative recombination that I create an electron hole pair in this material, and eventually I have this exciton, this electron hole pair, to recombine and emits again the energy in terms of luminations. I don't want that. So these excitons, these electron hole pairs, need to find an interface as soon as possible. So instead of using the typical p-n junction architecture of organic solar cells, I use what is called the bulk heterojunction architecture. That means I mix P3HT and PCBM at the nanoscale in a way that the typical scale length between the various components is of the order of the exciton diffusion length, that is a few nanometers, while in silicon can be several microns. So here we go. And I have here at the end a whole transport layer or electron blocking layer just to give a direction to the diode and make sure I don't have parasite recombination of the carriers. That's a typical solar cell. And then here I have my layer of ITO and graphene. How we see the one thing that is important is that I don't have contact resistance between this active layer and my electrode. So the work function of these two, the electrochemical potential of these two, has more or less to be the same. A way we study this work function, this electrochemical potential, is through Kelvin probe microscopy. That is a technique that is able to probe literally, to image the work function of a material at the nanoscale. So basically what you have is that in principle, you can even use conducting IFM if you have a flat surface. You have a probe that has a certain work function. You have a contact resistance between your sample and your work function. Locally, you have a diode. From the turn-on voltage of the diode, you know the difference in work function. In principle, I say, if you have a flat material, that works. The problem, if you have a material with wrinkles, roughness, like you have a graphene flake or a graphene-RNA nanocomposite, is that you have, in these cases, you have regions in which the electron emission, the contact resistance, is lower due to the conformation, due to the morphology. So people circumvented this problem instead of using just DC current measurements, having an alternate current measurement system that is known as Kelvin probe. So basically, you used your conducting sample at your tip to make a capacitor where the two plates have a variable and oscillating distance, and you are measuring the charging and discharging of this capacitor that is proportional to the difference in voltage that you measure in this case in AC at a specific frequency. That's basically the principle of Kelvin probe. If you measure the work function of graphene in this way, you see that it depends dramatically on the number of layers, but never reach the work function of graphite. Why? Because the work function of graphite is in a way a bulk effect, or at least a few layer effect. Here you have just one layer that can be oxidized because you put it in water for your solution processing. Even if you don't have graphene oxide, for graphene oxide can be even lower, this work function, the work function is not really the work function of graphite. It's lower. And that's a problem for one reason, because one of the reasons why people started to use these materials as transparent conductors is that the work function of graphite is close enough to the work function of indium tin oxide that we have said is the transparent electrode you want to replace in these cases. And that's quite a situation. It's higher indeed. So while I have good electron hole transfer between these conducting polymers that form organic solar cells and indium tin oxide, if I have my work function of solution processed graphene that is higher up, so lower in absolute value, the transfer is much more difficult. I have a contact resistance. So the performance of my solar cells is lower. These materials go better than graphene oxide, not only because they are less defective, but because they have a work function that is a bit better, bit higher in absolute value. But still is not the ideal one. And you see when you do a solar cell, an efficiency of an indium tin oxide solar cell, I mean, done not in the most sophisticated possible way, you can do much better, but is about 3% with P3HT. For graphene solar cell, it's about 1.3, 1.5. Because of this mismatch in the Hall function of the electrode. And you can see also that this is reflected by this mismatch in Hall function by a higher contact resistance between the active material and the electrode. That means a higher series resistance if I make a diagram of my solar cell. There is another interesting thing of these solar cells that I want to say that when I discovered it, I was pretty shocked, is that while an indium tin oxide solar cell has very little dependency of the efficiency on the inclination of the cell compared to the incident light, because the transparency of transmittance of indium tin oxide is pretty constant, the transmittance of these materials, when I go away from normal incidence, so from here to this way, changes a lot, because these materials are optically anisotropic, because graphite is an intrinsically anisotropic material. So if I am turning the sun like from midday to 3 p.m., my efficiency go down much faster. While if I am really at normal incidence, sometimes they go better. So you see, these cells go better than ITO solar cells between noon and 2 p.m. But they start to get worse after 2:33 because suddenly graphene realized that it's also absorbing, because it's very transparent along the z-axis, but is strongly optically anisotropic and is much more absorbing along the plane, in plane. Also, the Hall function of these materials can be changed quite a lot depending on the impurities and on the treatment. You remember when I was talking about these treatments by nitric acid and thionyl chloride to make them more conducting. You say more conducting works better for solar cells. Yeah, in a way, yes, but I'm also decreasing the open circuit voltage, and that was another shocking thing, because the open circuit voltage of a solar cell should just depend on the band gap of the active material. But here we go, the active material is an organic material with pi electrons. The electrode is graphene with pi electrons. Pi electrons notoriously conjugate. When you have a stacked graphite, you have an electronic band structure that is different from graphene. As a matter of fact, graphene is a zero band gap semiconductor, graphite is a semi-metal. And here the same. I am changing the electronic structure, I am changing the Hall function, I am changing the entire structure of my solar cells. So I cannot talk anymore about a solar cell made by an electrode and an active layer. Here I have really a total heterojunction of the electron and the active layer that are really mixed up in a big soup. And I can see, this is another experiment, mixing graphene with a polymer. I tune the Hall function of the two, literally. It's not just that I have, as I would expect, the lower one. I have a mix of the two, if I do it by Kelvin probe or other things. So I will just briefly conclude saying that another thing that are important is these things are defects. We have talked about ideal graphene. When I oxidize it, when I put in water and so on, I'm making defects that are different. And also these platelets have intrinsic defects many times at the edges. And these defects are very, very little understood. That's why we did a job also to try to divide these graphene flakes in stripes, cut it to increase the defects at the edge, to study them, understand them a little more, also with the objective to try to discriminate the effects that are related to defects in the tissue of graphene, like vacancies, and defects at the edges. So I will skip about this. And let me go just to the summary, since I'm a bit out of time. And I'm sorry for the ones of you here, you have tremendously good EPR groups that work, you know, on the coherence of spins and so on. I'm a bit sorry that, I mean, this is a different topic. Perhaps we want to see what they don't want to see and vice versa, like defects that for us work as non-radiative recombination centers in solar cells work probably extremely well for quantum computation and vice versa. But it's nice, I had a couple of nice conversations about this here, so that was another exciting reason to be here, because sometimes with diverse environments and diverse situations you learn much more than reading more papers on your own subject and repeating your experiments over and over and over. So in summary, I told you a little about the preparation of these graphene platelets and nano spaghetti and whatever by solution processing, and how I can make fields pretty big and pretty large. A little about the properties of these materials, thermal conductivity, optical properties, thermal conductivity, which one depend on intraparticle properties, so overlaps, which one of them, like electrical conductivity, just depends on how dense are my platelets. I shown you guys a little how we can make these films a little better than in the past, replacing graphene oxide with surfactant assisted exfoliation methods like with RNA. And I told you a little about organic solar cells from graphene thin films with a number of pitfalls and opportunities that this device hide, like, I mean, there are optical and isotropic, so maybe they're good as polar emitters that you cannot do with normal solar cells. There are, the wave function of the electron can be tuned, so there are a lot of things. And especially I would like to thank you again for your attention and for being here. Thank you so much.
I just wonder, right, so when you make that filtration film, right?
Yeah.
And measure all this conductivity property, are those reduced or just the native like oxide you just prepare after the reaction?
Okay, depends on from situation to situation. I mean, many times we have done everything, from vacuum filtrating everything in anhydrous solvents in ways that they are different from what I described. So you don't have water and RNA, you have an anhydrous solvent and an anhydrous surfactant. You do everything inside a glove box, and you measure the thermal conductivity there from things that you measure outside. Right. Since the contacts don't matter a lot, also the surface oxidation doesn't matter too much. Too much means that it determines the conductivity of the individual flake. In fact, if I treat the flakes, you have seen that I can do different things. If I oxidize them like graphene oxide, the electrical conductivity goes down. If I dope them, if I can call that doping with thionyl chloride or these things, the conductivity goes up. But mostly they affect the electrical conductivity of the individual flakes, not the junctions.
And when you have those overlapping layers, right?
Yeah.
So are those like, do they form like a bond between them, or actually just loose contact?
Okay, what's your definition of a bond?
Chemical bonding, like between the graphite, right? Like
Van der Waals forces between graphite plates. Yeah,
right?
Is a weak bond, of course, van der Waals forces, yes. Yeah. If you're saying chemical bonds, like the ones in plane of graphite, no. That's why I say, what's your definition?
Final one.
Yeah.
So why use RNA, not DNA? Like,
DNA has not the phosphate groups, right?
It does.
Yeah. And on the other hand, oh yes, you're right, but has another thing, has a two chain, while there you have you need an individual chain. Sorry for the mistake, yes, you're right. But the charge transfer is much smaller. Yes, you're right, it has the phosphate group, sorry about that. But you have much less charge transfer because you have the double helix. I mean, you can do something. There are some interactions. For nanotubes, it's great because DNA has the chirality, and you have the right chirality to wrap around the right chirality of the nanotube. You sort nanotubes. But in a case like this, it's more difficult. Right. It's more difficult, and you want to have a high charge transfer. So you want to have phosphate groups and you want to have some uracil or something that also has a pretty good charge transfer. You want really to reduce the surface energy to exfoliate into this. This is an high chiral. If you want the short answer is RNA is not chiral as DNA is, and graphene has no chirality.
Laura?
So the choice for RNA is very intriguing, but as a molecular biologist, I mean, RNA is the scariest, most unstable molecule that I could possibly work with, and it has such a terrible tendency to secondary structure. So how do you maintain your RNA in some kind of somewhat of a uniform structure? Because it wants to create loops and all.
Yeah. Sometimes you have seen that when it wants to create loops, it works even better because remember the two situations I've shown you, of the two types of RNA I've shown. One doesn't create much loops, and the other creates a lot of loops. What you can do to optimize the amount of loops, and it was my initial thought at the beginning when my student Faranak started the project, I said, remember that the first thing we have to do is to pitch the pH of the solution to make RNA to disentangle as much as possible. She tried and wasn't working. And she picked on me for 1 month saying, why the thing that you are saying was working doesn't work, while the one that you are saying that didn't work works for me. You are a bad supervisor. And the answer was that some degree of entanglement works because it gives some buoyant forces for keeping graphene dispersed in water. I mean, is something literally like RNA is very soluble in water. It's one of the few things, much more soluble than graphene anyways. And at the same time has this very strong adhesion towards graphene molecules.
Right.
And that's
but our universe is so full of RNases that RNA is very, like, it's so readily degraded. And I just wonder about, you know, in terms of applicability.
well, certainly you need to do your application quickly, and there is another thing. I see also the opportunities. Since it interacts with a lot of things, you can use this as a template to attach to graphene things that otherwise they won't attach to graphene. Because graphene is not that you can functionalize it with everything. One thing at graphene as the magic material, but putting something functionalized, okay, the edges are pretty reactive. Everybody of us knows that. But I was talking at the beginning of my graphene experience with a chemist. He says that attaching something in the center of something that is so flat like graphene is like you need really to, it's like hanging on a mirror or something like that. One word, maybe this example. With RNA, it's exactly the opposite. It's like you have a spider silk. But at the same time, this spider silk sticks very well on graphene, perhaps probably because it's a spider silk. DNA is not that way. In fact, we tried at the beginning, and may work with nanotubes, and I also tried to get some DNA with a synthetic chemist that was synthesizing it, and he was trying, then RNA was working much better.
Right, and how did you choose where to get your RNA from, right?
At the beginning, we choose it randomly. Okay. Then, little by little, with some dynamic light scattering and other things, we started to understand the situation that you have to have the optimal pH for some disentanglement, but you have not to be completely disentangled. It's really a trade-off. I mean, if it gets completely disentangled, works greatly for exfoliation. I have a lot of individual layers, single layer graphene. But at the end of the day, I don't get rid of it in full. And I do a terrible vacuum filtration because my layers don't go up like a puzzle because they tend to stick together, make chunks, clumps. I don't know. They tend to do other things. Yeah. I mean, you see when you do a lot of nanoscopic investigation. But at the same time, I mean, yes, I understand, but I see it more as an opportunity because it's a scaffold to attach something to something that is like like a mirror, so it's very difficult to hang on
And
it.
at the same time,
Yeah,
be
yeah.
a scaffold that's
Yeah,
easily
yeah.
removed so that you'll-
But on the other hand, if you want to get rid of it, you just heat it up or use some strong acid, they will go in full.
hand on it.
Yeah. Sure, why not? Sort of.
If I can ask one, I think I saw that for some of your conductivity measurements on single sheets of graphene that high electrical conductivity corresponded to low thermal conductivity.
Yes.
Which is exactly what you want for a good thermoelectric material.
Yes.
So have you measured the Seebeck coefficient?
I haven't, but there are reports of people who are proposing these films for this. That means, without measuring, they didn't do a nice job. It will be a nice, yes, it's a tremendously good application because it's exactly what you want for a thermoelectric material. In fact, people are more considering, I've seen the most recent one there in the literature, functionalized graphenes, like nitrogen-doped graphene, where probably this effect is even stronger. But yes, people are thinking on it. Good point.
Any further questions? If not, let's thank Dr. Fanchini for an excellent lecture.